Hey everyone, and welcome back to Medical Minis. This is part 5 of our series on understanding the basics of ECG going from 0 to hero. In our previous video, we discussed the basic ECG trace. So if you didn't watch that video, please make sure you do. And in today's video, we are going over how the ECG trace corresponds to the heart, and more importantly, the idea of net vectors. So without further ado, let's get started. So now here we see a very normal ECG trace. Okay, we have all the relevant waveforms, the P wave, the QRS complex, and the T wave. And here we see all the relevant structures of the heart which lead to these particular waveforms. The P wave, which is also known for atrial depolarization, deriving from the SA node. We have the QRS complex, generally known to deliver ventricular depolarization. However, more specifically, it is responsible for septal depolarization through the septal fascicle and ventricular depolarization through the Purkinje fibers. And then finally, the T wave, which is responsible for ventricular repolarization. Okay, so before we start understanding the concept of net vectors, we first need to be aware of one particularly important lead, and that's lead 2. Now, the reason lead 2 is so important is because lead 2 gives the best measurement in terms of the general movement of the impulses of the heart. And why is that the case? Well, as we have mentioned in previous videos, especially my video on the leads, and if you are still unsure about the leads, please make sure you look at that video. So generally, the movement of impulses of the heart go in this particular direction, okay? And what do you see from lead 2? Well, lead 2, as we know, with all bipolar leads, we measure from the negative to the positive. And so lead 2, as you can see here, best matches the general movement of the impulses of the heart, okay? So that's why lead 2 is very important, and especially in terms of net vectors and understanding how they work. So now let's start getting accustomed to the idea of net vectors. Firstly, we have the SA node, the AV node, the bundle of His, the right and left bundle branches, which gives off certain fibers, and then we have our Purkinje fibers. Now, like I said, one of the most important leads is lead 2. It's a very powerful lead and is one of the most informative leads because it follows the natural or physiological movements of impulses from within the heart. Now let's begin by looking at our first wave, which is the P wave. Okay, so with the P wave, you can see I have drawn a net vector. And so with the P wave, you can see here that I have already drawn a net vector moving from the right to the left atrium in this particular direction. Now, let's start talking about why do we actually get a P wave that looks something like this and not something like this? Or why don't we get something like this? Well, if you've looked into my previous videos, we've discussed the idea of deflections. So for example, this is a lead and our impulse is moving in the same direction. What do we have? We have a positive deflection. If it's moving in a perpendicular fashion to the lead, we have a sinusoidal 50-50 wave. And if it is going in the opposite direction, we have a negative deflection. So what do we have here? Well, as you can see here, it is almost pretty much parallel. And so this is why we actually get a positive deflection like this. But you may be saying, why does it actually move like this? What's making this atrial depolarization move in this particular direction? Okay, so let's talk about that. So I'm going to draw a quick diagram to illustrate why do we get this particular movement. Here we have our SA node, and here is our impulse going across the atria from the right going towards the left. So we know generally there is going to be a net vector going from the right side to the left side. That's fine. However, to better understand net vectors, you should understand a wave can be thought of as individual linear vectors. So if we were to represent this in terms of linear vectors, it would be something like this. Here is one vector, here is another one, here's another one, here's another, here's another, and another one, and another one. Okay, so instead of this diffuse kind of general wave of depolarization, we can think of this wave as individual vectors causing this wave. Okay, and now hopefully you will start to understand the idea of net vectors. Okay, net vectors just basically means a total summation, or let's say the mean or the middle value, right? So if I was to say which one of these arrows best represents the middle or mean or the net vector, hopefully you would say it's this one. And so this is why we get a net vector in this direction. Alright, so now let's move on to the Q wave. So here is our P wave, and here is our Q wave. And you will notice that the Q wave is a negative deflection. Now, hopefully you will understand that negative deflection comes from the idea of an impulse moving away or in the opposite direction to our lead. In this case, lead 2, as we can see here, the impulse is, you could say, sort of moving in the opposite direction, at least more than in the perpendicular plane. Okay? And so this is why we have a negative deflection in lead 2. Now you may be wondering, okay, how do we actually get this direction, this vector? Well, let's now have a look. Okay, so now let's start discussing why do we actually get a septal depolarization vector moving in this particular direction. Well, the reason you may have spotted, we actually have a septal fascicle. And the septal fascicle, as you can see here, derives from the left bundle branch. Okay, now that's one thing you can keep in mind. However, there is also another theory to why we have septal depolarization moving from the left to the right. Now this is something I came across, and it's to do with these insulatory sleeves you have around each bundle branch. So if this is my right and left bundle branch, the right would have a intact insulatory sleeve. However, it's been proposed that the left does not have an intact sleeve, rather sort of this septated or have gaps in the sleeves. Okay, and as you can see, the sleeves are on one side and not on the other. And so you can now imagine, once we have our depolarizing wave coming from the AV node down the bundle of His, and it travels through each bundle branch. Okay, once the left bundle branch is activated and releases its impulses, it can actually pass through these gaps, okay, in the insulatory sleeves, moving in this particular direction. And so this has been proposed to which why there is a impulse moving in this direction through these so-called gaps in the insulatory sleeves. Now, again, this is a theory. I'm not too sure on the validity, but yeah, it sort of makes sense to me. So now, tying things together, our negative Q wave is because our septal depolarization moving in this particular direction is moving in a opposite, more or less, direction towards lead 2, and so we have a negative deflection in our Q wave. And now we move on to the ventricular depolarization, or as I like to think about it, the RS wave, and not the QRS, because now you guys know what a lot of people don't. The Q wave is actually responsible for septal depolarization and not exactly ventricular depolarization. So now, as you see in the white, we have a net vector that is moving sort of towards the left ventricle rather than the right. And so my question is, why doesn't this vector move more towards the right side? Well, the answer is in anatomy. The left ventricle, as we know, is larger than the right ventricle, and you can imagine the left ventricle has more cells, more myocytes, more contracting cells, and so therefore more of the impulses is needed on this particular side. And so that's why we have a skewing towards the left ventricle. So what exactly happens? Okay, so I'm going to draw an image again to represent this movement. So we have our AV node, our bundle of His, our right and left bundle branches. We have our left fascicles, our posterior, and our anterior fascicle, and our right fascicle here, and they give off our Purkinje fibers. Now, what's going on in terms of the impulse? Now, as we have already said, septal depolarization moves in this direction, so that's fine. And then the impulse will continue down and through our Purkinje fibers, give off impulses like so. So here is these micro vectors, you could say. And now if I was to mention, if you were to give a net vector, where would the net vector go? Well, you would need to take into consideration the anatomy. Like I mentioned, we know that the left ventricle is much greater in size than the right, so it has a lot more cells, and these cells need a lot more of the impulse. And so generally the net vector will be skewed towards the left, and so therefore our net vector is in this direction. And now in terms of the amplitude, why is our R wave so big? So here's our P wave, which we already mentioned is a positive deflection, a negative Q wave, which we have already mentioned, and then the R wave. Why is it so large? Well, it's so large because of the ventricle. We know that, well, the ventricle is very big. And that's the reason why we have such a strong amplitude in our ECG. That is why we have this very large R wave. Okay, so that's why we have a large R wave. And why is it positive? Well, it's positive, as we should know by now. Look at the direction of the impulse. How does it relate to the lead? Well, it's moving in the same direction, so it's a positive deflection. And so that is our R wave. However, things still carry on. We have another wave, which is the S wave. It goes down, and then sort of a negative deflection here. Now, where does this S wave negative deflection come from? Well, let's continue with this diagram. As you can see here, the impulse will travel from apex to the base of the heart, of course, because we need all the blood from the apex to the base to be squeezed out. So the contractions will then begin to climb up the heart. The net impulse in this particular phase of contraction will be in this sort of direction, okay? Right? And so in perspective to lead 2, it is going in the opposite direction. And so because it's going in the opposite direction, that is why we have a negative deflection in our S wave. And finally, we have our T wave, or ventricular repolarization. Now let's recap. We had positive deflection in P wave, negative deflection in our Q wave, strong positive in our R wave, negative in our S wave, and now we have T wave, which is a positive deflection in perspective to lead 2. Now, as you may have already seen or spotted, that the net vector for T wave in this orange arrow is moving in the opposite direction to lead 2. Now, you may be thinking, surely this should be a negative deflection because, wait, you told me that if a wave moves in the opposite direction, it's a negative. Well, I would say yes, that is true. However, there is an exception for repolarization. I have talked about this in my previous video, so I won't get into the physiology behind this. However, just to mention that the reason for this is because in repolarization, what are we doing? We are transforming the depolarized state of the heart back into a repolarized or non-polarized state. So what does that mean? Turning the positive charges back into negative charges. Okay, so this is the concept behind why we have a positive T wave. In any other case, in any other situation, yes, it would be a negative deflection. However, because of this phenomenon, we say that it is a positive deflection. Alright guys, so that's the end of the video. I hope you enjoyed. Today, in summary, we've discussed how do we actually get the P, QRS and T waves through the concept of net vectors. In our next video, we will now be putting everything we've learned together, i.e. looking at the systematic approach. So if you guys enjoyed, please leave a like and subscribe, and I'll see you guys on the next video.